Good. Good evening, everyone. We're here for another session, obviously, of our technician licensing class. And today's topic, if I can get it to advance, there we go. Today's topic is going to be related to antennas, which is really a very important topic. You will find as time goes on that you're constantly talking about and concerned about antennas. So this session, it's divided down into a number of subtopics. We'll talk about antennas and feed lines. We'll talk about vertical and horizontal polarization, the patterns produced by a dipole antenna, the concept of antenna gain, beam antennas or directional antennas in general. Talk about antenna loading, differences in portable and mobile antennas. Talk about the resonant length of an antenna and how that's related to frequency. We're going to be talking about types of feed lines and concepts of attenuation and how it varies with frequency and selection of feed lines. We'll talk about the concept of SWR, standing wave ratio. Talk a little bit about antenna tuners and RF radio frequency connectors, what connects coaxial cables and antennas together and radios. So those are the main topics. Some quick definitions here. An antenna is an object that facilitates the sending of the signal to some other station. The feed line is what connects your station, your radio, to the antenna. Test and matching equipment are pieces of equipment that allow you to monitor the performance of your antenna. The feed point is where the transmitted energy enters the antenna. The element of an antenna is a conducting part of an antenna, but it could be more than one part or parts of an antenna, and it's what's designed to radiate or receive the radio waves. There are a couple of kinds of elements. A driven element is the element that's supplied directly with power from the transmitter. That's where your feed point would be, and your driven element, that's where the power enters the antenna. Polarization is the direction of the electric field. If you'll remember the concept of the electrical fields and the magnetic fields of an RF wave, we're looking at the direction of the electric field relative to the surface of the earth. So if it's parallel to the surface of the earth, it's horizontal. If it's vertical, perpendicular to the surface of the earth, it's vertical. It's the same polarization. The direction of the electric field is going to be the same as the physical direction of the antenna, and we'll get into that. Yeah, right. So some other definitions and abbreviations. dB is decibel. dBd is decibel with reference to a dipole antenna. dBi is decibels with reference to an isotropic emitter. ERP is short for effective radiated power. You'll see us using F for frequency here. HF is high frequency. The Greek letter lambda is used for wavelength. MHz for megahertz, SWR for standing wave ratio, and of course UHF and VHF we already familiar with, as well as the Greek letter omega for ohms. Okay, so the first subtopic we're going to cover is vertical and horizontal polarization and dipole patterns. So if you look at an antenna, there's a lot of ways you can sort of classify antennas. We can talk about their shape, their gain, their directivity, the impedance that they at their feed points, whether they're short, whether they're flexible, all kinds of ways that you can describe antennas. The three things that we kind of care about, certainly for the exam purposes, are orientation, directivity, and size. So orientation, as I just mentioned, horizontal means parallel to the earth, so it's going to be a horizontally polarized antenna. Vertical means perpendicular to the earth, which would make it a vertically polarized antenna. directivity, which we'll get into, beam antennas like Yagi antennas and others, and size relative to wavelength. So you can see the examples listed here. We talk about a half wave antenna, a quarter wave antenna, a 5/8 wave antenna, and so on. In other words, the length of the antenna or the size of the antenna in relation to a wavelength or for a particular frequency. So that's ways of describing or classifying antennas. Common type of horizontal antenna is your half wavelength dipole antenna. And this is an illustration of what one looks like. And when we say it's a half wavelength, we mean that the total length is equivalent to a half of a wavelength for whatever frequency it's going to operate on. And you can see that it's fed here in the middle. You can see we have like an open wire feed in the center, some spacers to keep the wires apart, comes into an insulator, and one half of the feed goes off to the right, the other half of the feed goes off to the left. The right side is a quarter wavelength long, the left side is another quarter wavelength long. The total length would be a half a wavelength. And going back to our formula for wavelength, we know that 300 divided by the frequency in megahertz will give us a wavelength in meters. So for a half wavelength dipole, a half wavelength dipole length in inches would be the wavelength divided by 2, because it's a half a wavelength, times 39 to convert meters into inches. You'll see us as we go through some examples of this. So this type of an antenna is going to produce this kind of a radiation pattern. So that red horizontal line represents the dipole antenna. And we're looking at this down like from the top. So the antenna is there and we're looking at on the top of it. The energy radiates out from the sides of that antenna, not from the ends, from the sides, broadside to the antenna. And you can see this radiation pattern as you look at it from above. If you were looking at it end on, it would look like a donut around the wire. This pattern is what it looks like if the dipole is placed about a half wavelength or more above the ground. If you move it closer to the ground, there's reflections off the ground, which distorts this pattern. And eventually it gets to, when it's really low, it's more of an omnidirectional than this sort of donut pattern. But this is the kind of important thing to remember, is that the energy is broadside, emitted broadside to the antenna. So if you want to take a look at a vertical antenna instead of that horizontal one, then this is an illustration of sort of 3 situations with vertical antennas. I do want to kind of get back to the length for just a second, though. When I say it's wavelength, it's actually going to be slightly less than the actual wavelength calculation that you have. And that is because electrons flowing through a conductor are actually slower than the speed of light because of the resistance in the material. This decrease is called the velocity factor, and it's usually expressed as a percentage. So for example, like copper, which would be a common conductor for an antenna, especially a wire antenna, it's about 95 or 95% of the speed of light, which also means that an antenna made of copper will be about 95% the size of the theoretical value. So they're going to be a little bit shorter than the actual theoretical wavelength, whether it's a horizontal or a vertical antenna. So looking here at the vertical antenna, you can see we're talking about here a what we call a quarter wavelength vertical. And in one sense, it's a quarter wavelength, but in another sense, it's really the same as a half wave dipole, and I'll show you why that is. So let's take a look at the example on the left. You'll see that the height of this vertical antenna is a quarter of a wavelength, which would be like 1/2 of a dipole, right? But they don't have necessarily the other half. You have what's called a ground plane. And in this example, you have some radials coming out, and the total length of those radials combined ends up being a quarter of a wavelength. So that's like the second half of the antenna. Similarly, you can see in the middle picture, it also has radials for a ground plane. It's called a ground plane. They're pointing out more horizontal. The other ones were pointing down. And we'll talk about that in a minute. But you can see that it's a quarter of the wavelength of the vertical portion of the antenna. The rest of that antenna is the ground plane. And then the last one on the right is an example of an antenna it's called a Marconi antenna. It's doesn't have a ground plane made of radials. The ground itself forms the rest of the antenna, and it is a quarter wave on top. So that's a quarter wave vertical antenna. And this is the kind of pattern you get. This is a side view looking at the antenna. So it would be the antenna would be pointing like where it says 90 here. That would be the antenna here. And these would be the radiation patterns out from it. So if you had a perfect ground for it, you would see with this quarter wave, you would get this pattern here. That's the way the energy would be coming out from the vertical antenna. More typical, you get something a little bit squished down like this a little bit. Okay. From above, again, it's going to look like a donut. Because remember, now we were looking at horizontal was one way, vertical, which basically now we're looking down on it, it would look like the horizontal looked from the side. So what would be a perfect ground? Something like the center of a metal car roof with a VHF antenna would be that kind of a ground plane that would give you sort of this kind of radiation pattern. Okay. A standard quarter wave vertical antenna at the feed point, so which is going to be at the bottom of that antenna where the energy enters the antenna, it's going to have an impedance of around 35 ohms. If you change the slope of the radials, it will affect that impedance. So if you slope them downward, it will raise the feed point. And ideally, you want to have a feed point on an antenna. I mean, it would require you to do nothing. It would be perfect, would be a 50 ohm, because your radio is going to expect to see a 50 ohm impedance. And yet you would be using 50 ohm coax, so you would like to see a 50 ohm. You almost never have that. There's usually some difference, but. So let's take a look at some questions that relate to what I've just been talking about. And I'm going to be going through these questions in a different order than they're listed in the question pool. I kind of tried to group them a little bit more by these topics so that they're related questions or we'll talk at the same time about. There are two subsections to this T9 section. And on the exam, there'll be two questions from the section, one from each subsection. So there's not a lot of questions from this, but it's a kind of a short session today, or a short section today. But you can expect two questions total from all of these topics today. So let's look at the first one here. Which of the following describes a simple dipole oriented parallel to the Earth's surface? If it's parallel, it's horizontal to the Earth. So we are looking at a horizontally polarized antenna. Okay. In which direction does a half-wave dipole antenna radiate the strongest signal? Remember, we had that picture, and we said if you looked at our one end, it looked like a donut. From the other direction, we saw a pattern. And remember that the energy was coming off broadside to the antenna. So let's talk a little bit about antenna gain, beams, and beam antennas, loaded antennas, and portable and mobile antennas. So generally bigger antennas are better. Bigger is better. The most common types of vertical antennas you're going to find are a quarter wave, half wave, and 5/8 wave. And that's because they can be more easily matched to 50 ohms than some other lengths. Longer antennas will focus the energy lower and offer more gain in one direction. Gain is not an increase in power overall. You only got so much power is going to come out of your radio. When we talk about gain, we're talking about relative power in a particular direction. If you can think about a balloon full of air, there's so much air in it, but if you squeeze that balloon, you're going to have less air in one area, but it's going to protrude out in another, right? So it's going to bulge out. So that's what kind of concept we're looking at with gain. We're focusing power in one direction at the expense of the other directions. And you can see here we've got different patterns here. With your quarter wave looks like this, whereas a 5/8 you get these two lobes and one of them is quite low. So that would be really good, like if you had something, an antenna up high and you wanted to reach a lot of people over on the ground around you, it would be focusing the energy in that direction. All right. Beam antennas. Beam antennas are designed to focus the energy in a single direction as much as possible. So a beam antenna is normally going to consist of at least three elements. Certainly at least two, but generally three or more elements. And we have one that's called the driven element. Remember from the definition we talked about, that's the element where the energy enters from the feed line into the antenna. So you have a driven element here. So this is your driven element. This is your feed point and your feed line coming into it. This boom is just what's holding these elements on it. Okay. This driven element is typically about a half wave dipole normally. These other elements are referred to as parasitic elements because they do not have power going directly to them. They absorb and reflect or retransmit, if you will, the energy that strikes them that comes from the driven element. So a reflector is placed behind the driven element. Okay. It's going to reflect the power forward. In other words, the energy bounces back off of it and comes back in this direction. Reflectors are generally longer than about 3% longer than a driven element. And it's designed to focus this energy back, to reflect it back towards the driven element. And then we have one or more director elements, which will be shorter than the driven element, and they will help to focus like a lens does, to focus the energy in a particular direction. An example is a 5 element. This would be a 3 element Yagi. A 5 element Yagi would have a 10 to 12 dB gain over a dipole. In other words, more than 10 times the energy in one direction, but at the expense of the other directions. So antenna designers have to balance the forward gain, the front to back ratio, the bandwidth, feed point, all these different factors when they're designing an antenna. Some will be optimized for maximizing the forward gain. Others may want to have a more omnidirectional pattern. Depends on what the purpose of the antenna is. But this is the important concept. You've got a driven element, a reflector, and a director. It focuses the energy in one direction. And this is the kind of pattern. This would again be looking down at a Yagi antenna. And you can see here's the energy lobes. So it's got some in the back that goes past the reflector and a lot of energy going forward and almost zero on the sides. So the total amount is still the same. It's just pushed in one direction, if you will. So this free power or effective radiated power is what we call gain. And we measure it in decibels, usually in relation to a dipole or to an isotropic resonator. An isotropic resonator is a theoretical point source. And the difference between dBi and dBd is 2.5 dB. 2.5, if you subtract 2.5 from dBi, you get dBd. Manufacturers like to talk about dBi because it makes it sound like it's got more gain. That's why you got to read specs carefully. Okay, so this is a picture of a Yagi superimposed over that pattern, and you can see that this would be your driven element here, reflector back here, and these are all your directors up here, and it's focusing the energy in that one direction. Okay, another type of directional antenna is called a quad antenna. In this case, the driven element, which is right here, is your driven element, is actually a full wavelength, but it's a loop. So each side of it is a quarter wavelength. And then you've got a boom that holds another parasitic element over here. And it focuses the energy, another type of directional antenna. Loaded antennas. Example of a loaded antenna is probably if you have an HT, it's probably the rubber duck antenna on your HT is normally a loaded antenna. What they do is they wind a coil of wire inside the casing of that antenna so that the total length is actually physically shorter, so it doesn't take up so much room, but the electrical length is longer. It's not an efficient radiator. It does narrow the bandwidth, and it's not great, but that's one of the reasons why your little short rubber ducks on a handheld radio aren't that good. Picture in the middle is what's called screwdriver antennas. Again, it uses a motor and a wiper inside a coil to adjust the amount of loading depending what frequency you're on. This one here has one in the middle here has what's called a capacitance hat, which provides additional capacitance to counteract, because a coil, remember, is an inductor, so it counteracts some of that inductance to improve performance. And you're really a nerd if you drive around on a bicycle with an antenna like that. But all right, so exam questions. What is antenna gain? Additional power added. Remember, we do not add or subtract. Well, we do not add power. There are losses in your power. We do not add power. It's the increase in the signal strength in a specified direction compared to a reference antenna. Remember, it's in a particular direction. What is a beam antenna? It's not built from I-beams. It is an antenna that concentrates signals in one direction. Okay. Which of the following types of antennas offers the greatest gain? What have we just been talking about to produce gain? We've been talking about a Yagi antenna. Yagis produce gain. They're directional in one direction. What is an advantage of a 5/8 wavelength antenna for VHF or UHF mobile service? And again, we had an illustration of that. It has more gain than a quarter wavelength antenna. Remember, longer is better. Which of the following describes a type of antenna loading? Okay, so we just talked about how the rubber ducks have some antenna loading, and it's electrically lengthening by inserting inductors in radiating elements. It's that coil of wire I was talking about. Which of the following increases the resonant frequency of a dipole antenna? Remember the relationship between frequency and wavelength, right? So, and antennas are based on the wavelength. So if you want to increase the resonant frequency, you would decrease the length of the antenna. You would shorten it. It's an inverse relationship. What is the approximate length in inches of a quarter wavelength vertical antenna for 146 megahertz? Okay, so going back to that formula we had in one of the first slides, 300 divided by the frequency in megahertz, and we know the frequency in megahertz is 146, which gives you the wavelength in meters, approximately 2 meters, 2.05, a quarter wavelength. Your vertical antenna, it's a quarter wavelength divided by 4 times the 39 inches to convert from metric, ends up with 20 inches. You can approximate that in your head, actually. 146 megahertz is part of the 2-meter band. Quarter of 2 meters is a half. Half of 39 is 19 and a half. So what's our answer? The answer is 19. That's the closest answer. Okay, closest answer. What is the approximate length in inches of a half wavelength 6-meter dipole antenna? Well, once again, the same formula. 6-meter, we know, is 50 megahertz roughly, times the 39 inches gets you 117 inches. What's the closest answer to that? Closest answer is 112. Okay. What is a disadvantage of the short, flexible antenna supplied with most handheld radio transceivers compared to a full-size quarter wavelength antenna? Again, we talked about how inefficient that antenna is with that loading coil, a rubber duck antenna. So it has low efficiency. It may or may not be mechanically fragile, and it does not create, it's going to create, depending how you're holding it, it's going to be vertical or horizontal, depending on how you point the antenna. What is a disadvantage of using a handheld VHF transceiver with a flexible antenna inside a vehicle? Well, we didn't really talk about this, but just think about it. The signal strength is going to be reduced because you're inside a metal box, essentially, that's going to shield those radio waves from getting out. So the signal strength is going to be reduced. You don't want to use your HT inside a vehicle if you want to get good performance. Okay. Moving into our next subtopic, going to talk about feed lines, SWR, and antenna tuners. So amateur radio transceivers have a 50 ohm impedance output. This is important because it's different from some other uses. The coax cable for your TV system is not 50 ohms, it's 75 ohms. So it would be a mismatch with an amateur radio. So you wouldn't want to be using that because you want your coax and antennas to be as close to 50 ohms as possible to ensure the best transfer of power. If you get any kind of a mismatch in impedance, it creates what's called a standing wave, which is measured with a standing wave ratio. And you can measure that with a standing wave ratio meter or a directional watt meter. An SWR of 1 to 1 indicates a perfect power transfer. As the first number increases above 2.1, 2 to 1, modern transmitters typically have some automatic circuitry to reduce the output to protect it from damage, because that energy that's being reflected back from the mismatch can burn up your radio. All feed lines have a certain amount of loss from resistance through the system. And standing waves will eventually either be radiated or lost as heat in the feed line. That energy has to go somewhere. It gets reflected back. It's either going to have to radiate out on your feed line somehow, or it's going to generate heat. Somehow that energy has to be dissipated when it's transmitted into an antenna system. So there's different kinds of feed lines. There's an example here of coax and hardline. Hardline is, as the name implies, it's hard, it's rigid, it's very difficult to work with. It has an air core for insulation. More common is your coaxial cables, which have a center core with an insulator around it and a shield around it. So these are your two conducting elements, the core and the shield around it. And what happens when you have energy traveling through and you get a mismatch, you get what's called a standing wave. So as you can see here on this, you've got, oops, get my mouse in the right place. We've got energy going this way. If some of it gets reflected back in the opposite direction, when those two meet, you can see how they mix together and either amplify or reduce each other. So you get this wave that on top of the wave, if you will. And that's called standing wave. And you want to reduce that as much as possible. There's also loss in the system through your feed line, and it can be fairly significant, and it depends on the type of coaxial cable you use, because that's the most common thing you're going to use for feed line is coax. And as you can see, this chart's kind of busy, but we'll just take a look at an example here in a second. But losses increase with frequency. So the higher the frequency, the greater the loss in the feed line. These numbers here are based on a 100-foot length. So this is how many dB loss per 100 feet of feed line. And you can see it gets to be quite significant. Oops, back up here. You can see it gets quite significant. You can see we're talking about here with RG174, a 32 dB loss up at a gigahertz. That's, that's like 95, 98% loss, something like that. More common if you're talking about here in the UHF range with something like RG58, which is what you might find on your little mag mount antennas, you've got over 90% loss through that feed line if it's 100 feet long. So you want to keep your feed line short. What is standing wave ratio? Okay, just we're talking about that, and it's a measure of how well a load is matched to its transmission line. That's your standing wave ratio, SWR. What is the most common impedance of coaxial cables used in amateur radio? And that would be 50 ohms. That's what you want to keep everything at, 50 ohms. Why is coaxial cable the most common feed line for an amateur radio system? Talked about how hard line is to use. Well, coax is easy to use and requires few special installation considerations. It's more flexible than hard line. It's just easier to use. What is the benefit of low SWR? Well, if the SWR is low, it means your signal loss is going to be low. So that's the advantage. What happens as the frequency of a signal in a coaxial cable is increased? What did I say about that? What does it do to the loss? It also increases. Higher the frequency, the greater the loss. What can cause erratic changes in SWR? Well, it's not going to be your local thunderstorm or an overload from a local station. Because remember, the SWR has to do with how the energy is traveling through your antenna system. So if you have a loose connection in the antenna or feed line, it's going to cause erratic changes. If it's loose, it's going to make good connection, bad connection, it's going to vary, right? So that would be a loose connection in an antenna feed line. Which of the following is a source of loss in a coaxial feed line? Okay, well, obviously, high SWR would be a problem. And we also talked about connectors being a problem. So that's multiple connectors. So those are both issues. So the question is, would water intrusion affect? And yes, it would, because water intrusion will break down the insulation inside the coaxial cable. So actually, all of these choices are correct. Those are all things that can affect a coaxial feed line. What is the electrical difference between RG58 and RG213 coax? Okay, well, let's take a look at that chart we had. So we got RG58 and RG213. Let's take an example here at 400 megahertz UHF range. You can see that RG58 has an 11 dB. That's more than 10 times the loss. Yet RG213 only has a 4.8 dB. Right? See the difference there? So RG213 has less loss at a given frequency. Okay. Which of the following types of feed line has the lowest loss at VHF, UHF? Okay. Remember I said that the best one was that one that was difficult to work with, the air-insulated hard line. What is the major function of an antenna tuner? Okay, so we didn't really get into this. We're going to talk about it now. An antenna tuner or coupler, its function is to match the antenna system impedance to the transceiver's output. Okay, That's the purpose of an antenna tuner. We want the transmitter to see 50 ohms in that antenna. So what a tuner does is it makes the antenna system appear to be 50 ohms or close to it to the radio. So it matches the antenna system's impedance to the transceiver's output impedance. Okay. Last thing we're going to cover here is RF connectors. And this is pretty short here. Only going to be a couple questions. There's various types of connectors. There's just a bunch of different kinds of connectors you'll see on radios and on coax. Two important ones, I think, for the exam purposes are the N-type connector, okay, which is this one right here. And it looks pretty similar to the other type, which is the UHF or the PL259 connector. This is the most common thing you see for a plug, and then the opposite is the socket, SO239 socket. But the PL259 plug is the most common thing you see in ham radio. The N-type connector you will see more in commercial applications, but it's a much better connector, both for preventing water intrusion and for less loss at higher frequencies than the UHF connector. So our questions on RF connectors: which of the following RF connectors types is most suitable for frequencies above 400 megahertz? So we're talking about the UHF range, right? And what did I just say? The type N is the best in the UHF range. So above 400 megahertz, type N is better. The UHF PL259 SO239 most common, type N is the best above those frequencies. Which of the following is true of the PL259 type coax connector? And again, they are the most commonly used, and then we use them in HF and VHF frequencies. That's it for today. As I said, it's a little bit shorter section. Any questions on anything? Totally bewildered? Got it down thoroughly? I know when I studied for my technician, again, I was in the bewildered category, but okay, if there's no questions, then I guess that's it for this lesson. Let me